In a previous video, I talked about how to decompose partial fractions when the partial fractions had linear denominators. So in this video, I'm going to talk about when the denominators are repeated or quadratic. If you haven't already looked at the previous video or don't already know how to do partial fraction decomposition for linear factors, I would advise having a look at that. We are going to be using the same method. There are just a couple of slight differences. So if we start as we did before and first factorise the denominator. So x squared plus 2x plus 1 factorises down into x plus 1 times x plus 1. So I'm going to rewrite out my fraction, but with the denominator factorised. So x plus 1, x plus 1. So if I now do as I did before and split this up into our two partial fractions, we would have a over x plus 1, which gives us a proper fraction, using the first factor, plus b over x plus 1, again giving us a proper fraction, using the second factor of the denominator. Now, you might have already seen the issue with this one. We have two fractions here added together, but the denominators are already equal. So I could straight away just add them. A plus b, add the tops, and the denominators are equal, so the denominator stays as x plus 1. Clearly, a plus b, which are both constants, over x plus 1 does not give us 2x plus 5 over x squared plus 2x plus 1. So there is something wrong with this. We cannot do it in the exact same way. Now, this is what we mean by repeated factors. The two factors in the denominator of our original equation are the same, so they are repeated factors. So we have to do something slightly differently. So we can't have them both over x plus 1. So in order to get the x plus 1 times x plus 1 or x plus 1 squared in the denominator when we add them, one of the fractions must be over x plus 1 squared. Now, I know that might seem like we're not really splitting it up into simpler fractions, because we still have the same denominator in one of our partial fractions as we had in our original fraction, but it still reduces the top of the fraction down to just a constant, so it does still make the fractions easier for things like integration and differentiation. Now, I made a point last time that all the partial fractions had to be proper, which is how we knew that we had a constant on the top when we had a linear on the bottom, because it always has to be 1 degree less, or the highest power has to be 1 less than the denominator. Some of you may have noticed that x plus 1 squared, if we expanded it out, actually has the highest power of x squared. So you might be wondering why we don't then have an x on the top of the fraction. This is because each factor is actually only linear. So think of it as a linear factor. You just have to have the squared in there to show that it was repeated. So although it would still be proper with an x term on the top there, we don't need it because of the way we're breaking down and because each factor is just linear. We will look in a minute at what happens when you have a higher power on the bottom. So let's work through then and see what happens. So we follow the same steps as before, multiply through by the denominator of the left hand side, which leaves us with 2x plus 5 equals, I'm just going to write the full step out this first time. So we have x plus 1 times x plus 1, and that's still over x plus 1, and then we have b times x plus 1, and that is still over the x plus 1 squared, which is x plus 1 times x plus 1. Now hopefully you've noticed that one of the x plus 1's cancels in the a term, and both of the x plus 1 cancels in the b term. So this leaves us with 2x plus 5 equals a times x plus 1 plus b on its own, because everything else is cancelled. Now we can do what we did before and pick a strategic value of x to eliminate the a term, but there are no strategic values of x that we can use to eliminate the b term. So if for our first solution we let x equals minus 1, we'll do that first and then see what we can do for the b. So 2 times x, 2 times minus 1 is minus 2, plus 5 equals a times minus 1 plus 1 plus b. So 3 equals b. That gives us our answer for b, but how do we find our answer for a? We could pick another value of x, and now we know our answer for b as well. That will give us enough information. The only unknown would be a. The easiest value to pick would be to pick x equals 0. So 2 times 0 is 0, leaves us with just our 5 on the left hand side, and a times x plus 1 is just 1, so a plus b. B we now know is 3. So 5 equals a plus 3, so a must be 2. So our a is 2. So if we go back to our original partial fractions, we've got 2 over x plus 1, and b was 3, so plus 3 over x plus 1 squared. Now, if we double check this to check that it gave us our original equation, we only need to multiply the left-hand partial fraction by x plus 1 to get the denominators the same. So we end up with 2 lots of x plus 1 over x plus 1 squared plus 3 over x plus 1 squared. So that would give us 2x plus 2 plus 3 more, so 2x plus 5 over x plus 1 squared. So we know that those values are correct. The method would be very, very similar if we had a repeated fraction with a higher power than 2. So in this case, we've got 3 factors that are all the same. So we would actually have to split this fraction up into 3 partial fractions, one for each factor, with an increasing power on the bottom. So the first one would just be over x plus 2, the second one would be over x plus 2 squared, and the third one would be over x plus 2 cubed. You need to consider each factor, each possible factor, up to the highest power of factors. So remember, in the last video we talked about if there's 3 factors on the bottom, you need 3 partial fractions. You still need that, but this time you've got an increasing power each time. The reason for this can be seen if we consider something with numbers. So if we had 1/3 plus 1/9 plus 1 over 27, now 27 is actually the same as 3 cubed, 9 is the same as 3 squared, and obviously 3 is just 3. So if we wanted to add these up, we'd need to make the denominators the same. Now we'd need to multiply our first fraction by 9 over 9 to get the 27 in the denominator. We'd need to multiply the second fraction by 3 over 3 to get 27 in the denominator, and the last fraction is just 27. So this would actually give us 9, 10, 11, 12, 13 over 27. So our original 13 over 27, if we thought about splitting that up, we could split it up into its prime factors, which are 3 times 3 times 3. But one of the fractions was just over 3. One of the original fractions was over 3 times 3. And one of the original fractions was over 3 times 3 times 3. So we have to consider all those possibilities when we're doing it using algebra. We might end up with a equals 0 and that partial fraction might disappear, but we have to consider that all 3 of those factors might have been in the original question. Let's have a quick look at how we would solve this one then. So we do the exact same thing, multiply through by the denominator on the left hand side. So that would leave us with 7x plus 2 on the left hand side. That would be equal to a times x plus 2 squared, because one of the x plus 2's would cancel out, plus b times x plus 2, because 2 of the x plus 2's would cancel out, and then plus c. Now I'm going to solve this one in a slightly different way. We could, as we did before, pick x equals minus 2 to eliminate a and b and find c, but there are no values of x that we could pick that would then eliminate either a or b. So there is actually another way of doing it. I'm just going to first of all expand out all my brackets to aid us in the next step. So x plus 2 squared is x squared plus 4x plus 4 plus bx plus 2 plus c, and then I'm going to go one step further and expand it out again. So 4ax plus 4a plus bx plus 2b plus c, and that is all equal to 7x plus 2. Now the trick here is to realise that again this is actually an identity, so technically it should have an identity sign, but no one bothers writing that. Identities are hardly ever used. But what that means is that the left hand equation, the left hand side of the equation, has to equal the right hand side of the equation always. So at every single value of x, we are trying to find an identical expression up here, one that will always fit the left hand side of the original equation. So that means that on the left hand side of the equation we must have the exact same number of x squareds as the right hand side, the exact same number of x's as the right hand side, and the exact same number of constants as the right hand side, because all of them have to be exactly the same for the two equations to work for any value of x. So if we first think about our x squared coefficients, so what this means is the numbers in front of the x squared, and we know that the x squared coefficient on the left hand side, which we actually don't have any, must equal all the x squared coefficients on the right hand side. So this is actually our only x squared term, so a is our only x squared coefficient. So that straight away gives us the value of a, and we know that a is 0. Remember, to do partial fraction decomposition, our original fraction had to be proper. Because our denominator was cubed, we could have had an x squared on the top and it still would have been proper. So we might have ended up with a value of a had our numerator been different. But in this case, a is 0. We can then do the same for our x coefficients. So this time we do have one on the left hand side of the equation. We've got 7x. On the right hand side we've got plus 4x plus bx, and they are all the x terms. It's important to include the signs if you are thinking about them or ringing them as in I have. You don't have to ring them. I am just ringing them to make it clearer exactly what I'm doing, but it is important to consider the sign in front of each coefficient. So we know that our number of x's on the left has to equal the number of x's on the right. So I've got 7 on the left, and on the right I've got 4a plus b. Now luckily we already know that a is 0. So we know that b must be 7. So finally we then consider our constants. So we've got plus 2 plus 4a plus 2b and plus c. Remember, a, b and c are just constants, so 4a, 2b and c are also constants. So if we consider our constants, we know that we've got 2 on the left hand side, and that must equal 4a plus 2b plus c. Now luckily we already know that a is 0 and we already know that b is 7. So we've got 2 equals 14 plus c. So c must be minus 12. So if we go back to our original partial fractions, we know that a is going to be 0. So this whole term is going to disappear. B is going to be 7 and c is going to be minus 12. So my final answer is 7x plus 2 over x plus 2 cubed is actually equal to 7 over x plus 2 squared minus 12 over x plus 2 cubed. And again, you should check your answer. So I'm going to multiply my first term by x plus 2 to get it over x plus 2 cubed, and my second term is already over x plus 2 cubed. So I end up with 7x plus 14 minus 12, which is plus 2, all over x plus 2 cubed, so that is correct. Now I used a slightly different method here, which was evaluating coefficients, whereas previously in the previous video and the last question we chose strategic values of x to eliminate certain constants. Either method is fine. The evaluating coefficient method will always work. The strategic values of x method only works if you can actually eliminate constants. You could use a mixture of the two methods. So we could have actually used the strategic values of x and picked x equals minus 2, which would have actually eliminated a and b and given us a value for c straight away, and then we could have used the other method to find a and b. So test yourself, pause the video and have a go at answering this question, and I will give you the answer in a second. So the denominator of this one actually factorises into x plus 2 times x plus 2, or x plus 2 squared. So I'm going to write out my full compound fraction and two partial fractions. So remember, I need a constant over x plus 2 plus another constant over x plus 2, but this time that whole factor needs to be squared to allow for the fact that it is repeated. So follow the same process and multiply through by the denominator of the left-hand side, which will leave us with a times x plus 2, because one of the x plus 2's cancelled out, plus b. I'm then going to do it by choosing a strategic value of x. So in this case, if I pick x equals minus 2, that will eliminate a. So I will end up with minus 4 plus 6 equals b, in which case b equals 2. And then I'm going to choose x equals 0, and now I know a, that will allow me to find b. So I'll end up with 6 equals 2a plus b, which is 2. So a is 4 divided by 2, which is also 2. So if I go back to my original question, we've got 2 over x plus 2 plus 2 over x plus 2 squared. And remember that you should also multiply it back out and add it together to double check it. Right, now let's have a look at what happens when we have a quadratic factor in the denominator. So let's have a look at this question, that the denominator has already been factorised for us, and this part of the denominator doesn't actually factorise any further. So that is as far as we can simplify it. So when we consider our partial fractions, that will be one of our denominators. So remember from the last video I said that in order to do partial fraction decomposition, we need the fraction to be proper, in that the highest power on the top needs to be lower than the highest power on the bottom. Now some of you might be looking at this saying, hold on, the highest power on the bottom is squared, the highest power on the top is squared, so it's improper. But you need to consider this is already factorised. If it hadn't been factorised yet, so if we do the opposite and expand out the brackets, we would end up with an x times an x squared, which would give us an x cubed. So this is still proper, so we can continue. So our first fraction is going to be, as before, a over x plus 1. The bottom is linear, so the top is a constant, as it was before. This gives us a proper fraction. However, the second fraction is over x squared plus x minus plus 3. Now this is quadratic. The highest power is to 2, or we say it is of degree 2, which means that the top could be of degree 1. It no longer is certain that it is just a constant. We might actually have an x term in there as well, and it will still be proper. So we need to consider that by saying we might have b lots of x and a constant. This whole fraction here is still proper, but we need to allow for the fact that there might be an x term. Again, it might turn out to be 0, but we have to consider that it might be there. So let's work through exactly as we did before. So start by multiplying through by the denominator of the left-hand side, and that leaves us with 3x squared plus 5x plus 8 on the left-hand side, and a times x squared plus x plus 3, because the x minus 1's cancel out, and then bx plus c, you need it in brackets because it's the whole of the top, multiplied by x plus 1, and the x squared plus x plus 3 cancel out. So again, there are the two ways you can do this. Either pick some strategic values of x that eliminate each of a, b and c at a time, or do it by evaluating the coefficients. I'll do this one the first way by picking strategic values of x, and then we'll look at another example where we evaluate coefficients afterwards. So I can straight away see that if I let x equals minus 1, I'm going to make this bit here 0, which will eliminate my b and my c terms together and allow me to calculate a. So I'm going to first of all let x equal minus 1. So 3 times minus 1 squared plus 5 times minus 1 plus 8 equals a times minus 1 squared plus minus 1 plus 3. Now I could write out the rest of it, but I know that that's going to be 0, so going to be eliminated. So minus 1 squared is plus 1, so that's 3 minus 5 plus 8 equals a times 1 minus 1 plus 3. So we end up with 6 equals 3a, and a equals 2. So now I don't need to worry about eliminating a because I already know what a is, and it's going to be tricky to find a value because remember x squared plus x plus 3 doesn't factorise. So I can plug in my a value, which we now know is 2, and rearrange the equation. So I'm going to take this whole bit here over to my left hand side and rearrange the equation. So 3x squared take away 2x squared leaves me with x squared. The 5x take away 2x leaves me with 3x. And the 8 take away 2 times 3, so take away 6, leaves me with 2 on my left hand side, and that will leave me with my bx plus c times x plus 1 on my right hand side. Now from there I can see that actually if I pick x equals 0, I can eliminate b. So for this time I'm going to let x equals 0. So 0 squared plus 3 times 0 is 0, so that just leaves me with my 2, and that will leave me with c times 0 plus 1, which is just c, so c equals 2. Now I know what my c value is, I know that is 2. I can then simplify the equation down again and allow us to find our b value. Now we can pick any value of x that we like now because there is no value that actually eliminates c and makes it easier. We've already used -1 and we've already used 0, so I'm just going to use 1. As simple as you can. I'd use 0 if I could, but 0 would actually eliminate b. So if I let x equals 1 and I'm looking at this equation up here which has already been simplified with my a value, but I'm taking c to be 2. So 1 squared is 1 plus 3 times 1 plus 2 equals b times 1, which is just b, plus c, which I now know is 2, and that's all multiplied by 1 plus 1. So 1 plus 3 plus 2 is 6 equals 2b plus 4 if I expand out the brackets. So from that, take away the 4 to get 2, 2 equals 2b, so b equals 1. So that has given us our three values. So if we go back to our original partial fractions and write out the answer, a was 2, so we've got 2 over x plus 1, plus b was 1, so that's just 1x or x, and c was 2, and that is all over x squared plus x plus 3. So this here is our answer, and again you should multiply it out to check it. So let's have a look at another example, and this time we don't have a quadratic on the bottom, but we do have a repeated factor here and a normal linear factor here. So we are going to need three partial fractions, and we will end up with three unknowns a, b and c, but this time I will do it by evaluating coefficients rather than picking strategic values of x. So the first thing is to split it into its partial fractions. So remember our repeated factor, because it's a repeated linear factor, you only need a constant on the top, but you do need to keep the squared in the second one, and then our third fraction is going to be a constant over 3x plus 1. So they're all proper, but we don't need any x's on the top this time. So let's multiply through by our denominator, leaving us with 6x squared plus 25x plus 16 on the left hand side. That will give us a times x plus 2, because one of the x plus 2's cancel out, but it's also multiplied by the 3x plus 1, plus b times the 3x plus 1 because both x plus 2's cancel out, and then plus c times the x plus 2 squared, and the 3x plus 1 cancels. So this time I'm going to evaluate coefficients. So I'm going to first of all expand out my brackets to make life easier. So 3x squared plus x plus 6x plus 2 plus b 3x plus 1, and then remember x plus 2 squared means x plus 2 times x plus 2, so that's x squared plus 4x plus 4. And then if I expand out again, I get 3ax squared plus x plus 6x, so 7ax plus 2a plus 3bx plus b plus cx squared plus 4cx plus 4c. So I've just expanded out my bracket, and just to make life easier for myself, I'm going to rewrite out the left hand side of the equation here. So remember, to evaluate coefficients we do each power of x separately. We know that the left hand side we need the same number of x squared as the right hand side. So let's start by evaluating our x squared coefficients. And remember, you need to consider the signs in front of them. So I've got 6 on my left hand side, and that must equal 3a. This time we've got another x squared, so plus c on my right hand side. So I can't solve this yet because I don't know either a or c, so I'm going to carry on and evaluate my next coefficients. So for my x coefficients, I've got 25 on my left hand side, and that must equal all the x's on my right hand side, so 7a plus 3b plus 4c. So again, I've got 3 unknowns now. I can't solve it yet. So let's do the constants, and this time I've got the 16, and that must be equal to the 2a plus b, because that's also a constant, plus 4c, because that is also a constant. So now I actually have 3 equations and 3 unknowns, so we're going to need to solve them simultaneously. And this is where this method is slightly more difficult than the other method. It's easier to set up because you don't have to try and think of what values of x you need, but you do have to solve some simultaneous equations. So I can see that I have a, b and c in the bottom two, so I'm going to use my first equation to find a value for c. So c equals 6 minus 3a, if I take away 3a from both sides, and let's call that equation 4. So if I now sub this in to both of equation 2 and 3, I'll eliminate c, and I'll have 2 equations, 2 unknowns, so normal simultaneous equations. So I've got 25 equals 7a plus 3b plus 4 lots of c, which is going to be 4 lots of 6, which is 24, minus 4 lots of 3a, so minus 12a. And if I sub it into this equation, so into equation 3, I get 16 equals 2a plus b plus 4 lots of c, so again plus 24 minus 12a. So I can then simplify both of these two equations. So if I call them 5 and 6, from equation 5 simplifies down to 25 equals 7 minus 12, so minus 5a, and then plus 3b plus 24. So I'm going to take 24 away from both sides, which will leave me with 1 on the left hand side. And then from equation 6, if I simplify it down, I get 16 equals 2a minus 12a, so minus 10a, plus b, and again plus 24, which I'm going to take away from both sides, so minus 8. So I'm going to use the method of elimination by multiplying my top equation through by 2. So I get 2 equals minus 10a plus 6b, and I'm just going to rewrite out this equation. I haven't changed it, I'm just going to rewrite it out underneath. So minus 10a plus b. Now if I take my top equation and take away my bottom equation, I'm actually going to eliminate the a. So 2 take away minus 8 is 10. The a's eliminate, and then 6 take away 1 is 5b. So this gives me b equals 2. Now I've got b, I can go back and find a. So if I sub that into equation 5, I've got 1 equals minus 5a plus 3b, which is 6. So minus 5 equals minus 5a, therefore a equals 1. So I've got my b value, I've got my a value, so all that's left to find is my c value. And luckily I've got a nice equation up here which tells me that c equals 6 minus 3a, and a is 1, so 6 minus 3, which is 3. So now I have everything I need. I know that a is 1, b is 2, and c is 3. So again, you should check these, multiply it back out, and check that you get your original answer. So test yourself, pause the video and have a go at this question, and I will give you the answer in a second. So we first of all need our partial fractions. So we've got a over x plus 3 plus our second fraction is going to be over a quadratic because x squared plus x plus 1 doesn't factorise. So our top could have an x in it, so we need to consider this. So we've got bx plus c on the top. So when we multiply through by our denominator, we get 3x squared plus 6x minus 2 equals a times x squared plus x plus 1 plus bx plus c lots of x plus 3. And then I'm going to use some strategic values of x. You might have done it the other way, but you should end up with the same answer. So the first value I'm going to pick is going to eliminate bx and c by making x plus 3 equals 0. So I need to let x equal minus 3, which gives me 3 times minus 3 squared plus 6 times minus 3 minus 2 equals a times minus 3 squared plus minus 3 plus 1. This is where this method is a little bit more tricky and prone to error than the other method, because you have to make sure that you are squaring your negatives correctly and substituting incorrectly. So we don't actually need to write down our final term, because we know that the x plus 3 makes 0 and eliminates the bx plus c. So minus 3 squared is plus 9, so 3 times 9 is 27, minus 6 times 3 is 18, minus 2 equals a times minus 3 squared again is plus 9, minus 3 plus 1. So 27 minus 18 minus 2 is 7, and that's equal to 7a, so a equals 1. Now I'm going to do what I did before and substitute in a equals 1 and then simplify it. So I'm going to take away one lot of x squared plus x plus 1 from both sides of the equation, which means the left hand side of the equation now becomes 3 take away 1, so 2x squared plus 6x take away 1x, 5x, minus 2 minus 1, so minus 3, and that leaves me with my bx plus c lots of x plus 3. Now I'm going to eliminate the bx, so I'm going to choose x equal to 0. So if x equals 0, that just leaves my minus 3 on the left hand side, and that leaves me with 3c, so c is equal to minus 1. So the only term left to find now is b. I can't pick a value of x to eliminate c, so I'm just going to pick a value of x that I haven't used yet. So the easiest value is going to be x equals 1, because I've already used x equals 0. So 2 times 1 squared is 2, plus 5 times 1 minus 3 equals bx plus c, so 1b plus c, which is minus 1, multiplied by 1 plus 3, which is 4. So 4 equals b minus 1 times 4. So 1 equals b minus 1 and b equals 2. So now I have everything I need for my final answer, which is going to be a, which is 1 over x plus 3, plus bx, b is 2, so 2x, plus c, c is minus 1, so minus 1 over x squared plus x plus 1, and again just multiply it out to check your answer is correct. So I've covered repeated factors and quadratic factors. So just remember, for repeated factors you need to keep that squared in there. If you have x plus 1 and x plus 1 as your two factors in your compound fraction, you need x plus 1 and then x plus 1 squared in your denominators in your partial fraction. If you have a quadratic factor in the denominator of your compound fraction, then you will have a quadratic factor in the denominator of your partial fraction, which means that you have to consider the fact that you could have an x term in the numerator of your partial fraction. And there are two different methods of finding your values of a, b and c. One method by choosing strategic values of x, the other method is by evaluating the coefficients of the different powers of x, and sometimes a mixture of the two can actually be the easiest way. So I hope that made sense, and I will see you again soon.